Welcome to the Intro to Networks V7 for the Cisco Networking Academy. This video is Module 14, Transport Layer. The module objectives for Module 14 are going to be, we're going to look at transportation of data, TCP Overview, UDP Overview. We're going to take a look at port numbers, TCP Communication Process, reliability and flow control, and the UDP Communication. Transportation of data. The role of the transport layer is to transport data. It's responsible for logical communications between applications running on different hosts. The link between the application layer and the lower layers that are responsible for network transmission. If we're looking at the TCP/IP model here, it's at this layer right here. You have your network access, your internet layer, and then your transport layer. The transport layer has the following responsibilities. It tracks individual conversations. It segments data and reassembles segments. It adds header information. It identifies, separates, and manages multiple conversations. And it uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. In other words, you can have different conversations or different streams of information going at the same time on the same network. So you can have multiple video calling on the same network. IP does not specify how the delivery of transportation of the packets takes place. The transport layer protocols specify how to transfer messages between hosts, and they're responsible for managing reliability requirements of a conversation. And the transport layer includes the TCP and UDP protocols. Transmission Control Protocol, TCP, provides reliability and flow control. TCP's basic operations are number and track data segments transmitted to a specific host from a specific application, acknowledge received data, retransmit any unacknowledged data after a certain amount of time, sequence data that might arrive in the wrong order, and send data at an efficient rate that is acceptable by the receiver. UDP, or User Datagram Protocol, it provides the basic functions for delivering datagrams between the appropriate applications with very little overhead and data checking. UDP is connectionless. It's connectionless protocol. UDP is known as the best effort delivery protocol because there's no acknowledgement that the data is received at the destination. And if you know what the honey badger is, I call the UDP the honey badger of the protocols. It just don't care. It just sends its information. It doesn't care if it gets there or not. TCP, on the other hand, always makes sure that the data gets there or it retransmits. So TCP is reliable. It always makes sure that its packets get there. UDP, don't care. It just sends the information. So we need to have the right transport layer protocol for the right application. UDP is also used by request and reply applications where the data is minimal and retransmission can be done quickly. And if it is important that all data arrives and that it can be processed in its proper sequence, TCP is used at the transport protocol. So let's look at UDP here. Voice over IP, domain name resolution, or DNS. Those, we don't have to have every packet. So for voice over IP, if you've ever been on a phone with somebody, a digital phone call, and they start breaking up a little bit and you start losing them, you're playing a video game and you get some lag, and not everything comes through and then everything jumps all of a sudden, those are applications that are using UDP. They just don't care if all the packets get there. They're just sending them as best effort. So a digital telephone, a digital TV service doesn't care if everything gets there. So they run that on UDP. TCP, for example, your email, you have to make sure all the packets get there or you can't read your full email. Worldwide web pages, you need to make sure that everything is on that web page that you requested. So those use the TCP protocol. It's reliable, it acknowledges, it resends lost data. So TCP is reliable, it always acknowledges, it's connection oriented. UDP is not reliable, but it's lower overhead and it's fast. So let's take a look at TCP. TCP establishes a session. It's a connection-oriented protocol that negotiates and establishes a permanent connection or a session between the source and destination devices. It ensures reliable delivery. So for many reasons, it's possible for a segment to become corrupted or lost completely for any number of reasons. So as it's being transmitted over the network, if that happens, TCP ensures that each segment that is sent by the source arrives at the destination. If it doesn't, it resends it. It provides same order delivery because networks may provide multiple routes to a destination. They can have different transmission rates. Data can arrive in the wrong order, so that puts it in the correct order. It supports flow control. Network hosts have limited resources, memory, and processing power. So when TCP is aware that these resources are overtaxed, it can request that the sending application reduce the rate of data flow. This is a visual look at the TCP header. It's a stateful protocol, which means it keeps track of the state of the communication session. TCP records which information is sent and which information has been acknowledged. And if we look at this here, we get our source port, our destination port, our sequencing number, our acknowledgement number, our checksum, our application layer data. And that size is going to vary because that's put on at the application layer. But this is a visual look at the TCP header. The header fields here: source port, destination port, sequencing number. You can pause this here if you want to read which each one of these are. I'm not going to lecture over each one of them. But if you want to pause the video right here and take a look at each one of these. Applications that use TCP. It handles all tasks associated with dividing the data stream into segments, providing reliability, controlling data flow, and reordering segments. So SSH, SMTP, FTP, HTTP, those are some of the protocols that TCP handles. Now let's take a look at UDP. Its features include the data is reconstructed in the order that is received. Doesn't care. It just sends it. As it gets it, it just reconstructs it. Any segments that are lost are not resent. There's no session establishment, and the sending is not informed about resource availability. So it just sends it like a fire hose if it has to. It just sends it and it goes, and if it gets there, it gets there. It's a lot smaller, you can tell. So you have your source, your destination, your length, your checksum, and then your application layer down here. Takes less overhead, and if you want to pause the video right here, you can. These are the 4 fields in the UDP header. Applications that use UDP: live video multimedia applications, simple request and reply applications, applications that handle reliability themselves, unidirectional communications where flow control, error detection, acknowledgments, error recovery is not required or can be handled by the application. Examples include SNMP and TFTP. So here's some of the applications here: DHCP, DNS, VoIP, voice over IP, video conferencing. Those are all handled by UDP. Let's switch gears here and look at port numbers. TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. The source port number is associated with the originating application on the local host, whereas the destination port is associated with the destination application on the remote host. We have socket pairs. The source and destination ports are placed within the segment. The segments are then encapsulated within an IP packet. The combination of the source IP address and the source port number, or the destination IP address and destination port number, is known as a socket. Sockets enable multiple processes running on a client to distinguish themselves from each other, and multiple connections to a server process to be distinguished from each other. So if we're looking here, we have our source, but we also have our port on there. So we have our source IP address, but then we also have our port. So you'd have a 192.168.1.7, port 80. So it knows which port to open up. We have port numbers. I'm going to put a link below in the description to a site you can go to see all of the port numbers. There's what we have well-known ports from 0 to 1023. Those ports are reserved for common or popular services. Applications such as web browsers, port 80, port 443, email clients, remote access clients. Defined well-known ports for common server applications, and enables clients to easily identify the associated service required. Then we have registered ports. Those go from 1024 up to 49,151. Those ports are assigned by the IANA to a requesting entity to use specific processes or applications. Those processes are primarily individual applications that a user has chosen to install, rather than a common application that would receive a well-known port number. And an example of that would be Cisco has 1812 for the Radius server authentication process. And then we have private or dynamic ports, and those go from 49,152 all the way up to 65,535. Those are if I can say that here, We're going to back up. Then we have private and dynamic ports, 49,152 to 65,535. The client's OS usually assigns port numbers dynamically when a connection to a service is initiated. The dynamic port is then used to identify the client application during the communication. These are some of the port number groups here. 20 for file transport protocol for data, 21 for the control, 22 for SSH. You can pause the screen right here to look at these, or you can check out the link below in the description. You can see what connections are on your system. This is on a Windows here. You can type the netstat, and this will show active connections. It will show the protocol. It will show the local address, the foreign address, or the destination, and the state, whether it's established or not. Sometimes it'll give you an IP address with the port, or it'll just tell you the HTTP here, or it'll tell you the actual site. But you can see what all connections are on your Windows machine. TCP Communication Process. Each application process running on a server is configured to use a port number. An individual server cannot have two services assigned to the same port number within the same transport layer service. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and processes segments addressed to that port. Any incoming client request addressed to the correct socket is accepted, and the data is passed to the server application. And we can see an example of this here. We have a client that's we send a request to the server, and we get a response back of the IP address, but source port 80, and then with the destination port. And then an SMTP would be on a port 25. So clients request a TCP server. Server responds to the TCP client use, and it uses the destination port for the request packet as the source port. So an HTTP request would get a source port of 49.152 and a destination port of 80. And over here for the SMTP, you'd get the same thing, except different numbers. When we connection or have a connection establishment, we have a three-step process. It's called the handshake. The initiating client requests a client-to-server communication session with the server. So we send a send signal, and it gives a sequence. The server acknowledges the client-to-server communication session and requests a server-to-client communication session. So the send gets received, and then the receiver says, oh, okay, I need to send now a send packet with an acknowledgement of packet, or an ACK packet, and this was sequenced at 200. This sequences it at 300, and it gives an acknowledgement of 101. So it took the sequence here and it put 1 on it, and then it gave it a control, and then it sent it back, and then the connection is established, and then the sequence is 101. Acknowledgement was 301 because it adds 1 to it, and then it does a control acknowledgement, and then the initiating client acknowledges the server to client communication session. So you have a handshake. So it sends, the receiver says, hey, I got this, let me send that information back to you, and then the sender gets a receipt back and says, hey, okay, now we've got a connection established. When we do the session termination, the process is reversed. When the client has no more data to send, it sends a segment with the fin or finish flag set. The server sends an acknowledgement to acknowledge the receipt to the fin termination session. The server sends the fin to the client to terminate the server client, and then the client responds with an acknowledgement. So it's easier for me to look at the visual here. So the sender sends a fin signal. It gets it. It sends an acknowledgement, says, hey, I got it. This acknowledgement received, and then it sends its own finish signal. So it says, hey, okay, I got that you're finishing, and I'm going to finish too, and sends a signal. And then the sender says, hey, I acknowledge that we're done. So this actually sends 2 receipts. It sends the acknowledgement plus its own finish signal, and then this closes its signal out, and then the session is terminated. So a 3-way handshake analysis. So it establishes that the destination device is present on the network. It verifies that the destination device has an active service and is accepting requests on the destination port number that the initiating client intends to use. It informs the destination device that the source client intends to establish a communication session on that port number. And then after the communication is completed, the sessions are closed and the connection is terminated. And the connection and session mechanisms enable TCP reliability function. That's what gives it reliability. Your urgent, your acknowledgement, your push function, your reset, your send, and your finish, or your synchronize. I call it the send, but it's a synchronized sequence number for numbering, and then your fin, or finished. Let's take a look at reliability and flow control. TCP can also help maintain the flow of packets so that the devices do not become overloaded. There may be times when a TCP segment does not arrive at the destination or it arrives out of order. So all the data must be received and the data in those segments must be reassembled into the original order. So sequence numbers are assigned in the header of each packet to achieve that goal. So the segments get sent 1, 2, 3, 4, 5, 6. Somewhere along the way they might have taken a different route up here on our routers. And so we get the packets back 1, 2, 6, 5, 4, 3, but this receiver says, hey, these segments have numbers in them and they're out of order, so we're going to reorganize those correctly. 1, 2, 3, 4, 5, 6. And then it's going to send it on up the de-encapsulation. No matter how well designed a network is, data loss is going to occur. So TCP provides methods of managing those segment losses. Among those is a mechanism to retransmit segments for unacknowledged data. So we start sending, so A is sending to B, so segment 1, segment 2, segment 3. Just as a quick note, if this was UDP, it would just send it and it would be done. But with TCP, this gets the acknowledgement, segment 3, 4, 5, 6, 7, 8, 9. Those get duplicated segments, and then it sends an acknowledgement 11. So it has to acknowledge the packets, or it resends them. So if 3 and 4 doesn't get sent, it will, if it doesn't get an acknowledgement for them, it'll resend them. So host operating systems today typically employ an operational TCP feature called selective acknowledgement. It's negotiated during the three-way handshake. If both hosts support SAC, the receiver can explicitly, it's hard for me to say, acknowledge which segments or bytes were received, including any discontinuous segments or segments that didn't. I know that's a big discontinuous. Why would they use a word like that? I don't know. It just means that segments that don't get there. 3 and 4 didn't get there, so it's got to be resent. So acknowledgement 3, and then we said 5 and 10 didn't, hey, we got 5 and 10, but 3, we acknowledged 3, and oh, hey, okay, so it's going to send 3, 4, because those didn't get there, and then continue on with 11 and 12, and reassemble them on the other end. TCP also provides mechanisms for flow control as follows. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between source and destination for a given session. And you can see the visual over here. If you want to pause your screen, you can see that it's using a window size to send, and if it becomes too much, it will slow it down or it'll change the window size. It's the part of the flow control process. The maximum segment size, or MSS, is the maximum amount of data that the destination device can receive. So a common MSS is 1,460 bytes when using IPv4. The host determines the value of its MSS field by subtracting the IP and TCP headers from the Ethernet Maximum Transmission Unit, or MTU, which is 1,500 bytes by default. So 1,500 minus 60, 20 bytes for the IPv4 header, 20 bytes for the TCP header, and it leaves 1,460 bytes. And we have a visual over here on the right side. Now, when we try to do congestion avoidance, when congestion does occur, or a lot of traffic on a network, it results in packets being discarded by the overloaded router. So to avoid and control congestion, TCP employs several methods to do that, timers and algorithms. So there's some different timers and algorithms that it does. So if it's not getting packets and it's missing a certain timer, it'll slow down. The sender will slow down a little bit, change its window size. So TCP segment 1 gets through, 2 and 3 doesn't. 4 gets sent, 2 gets the acknowledgement, and then it has to send 2 and 3 again. But it will do that congestion avoidance by timers and algorithms. UDP communication. UDP has low overhead versus reliability. It does not establish a connection. It provides low overhead data transport because it has small datagram headers and no network management traffic. So again, it's the honey badger. It just don't care. It's small. It's meant to be small. It's meant to not take up as much data traffic because there's a lot of information. When you're doing a voice over IP call or a video conferencing, there is a lot of data going through. So by using the UDP, smaller packets, you can get a lot more data through and you don't have to worry about packets being resent and having more traffic on your network. So that if you'll see that, if you've ever done that before and you've seen the breakup of the video a little bit, that's what's happening. The UDP packets just aren't getting through. UDP does not track sequence numbers. It has no way to reorder the datagrams in the transmission order, and UDP simply reassembles the data in the order that it was received and forwards it to the application. And then it's up to the application to try to make sense of it and to try to put it back together. So if it takes different routes, 1, 2, 3, 4, 5, 6, if it gets there in 1, 2, 6, 5, 4, lost datagrams are not resent. So if it loses one, if 3 is gone, the application will just try to make up for what's there or skip, or it's up at that point up to the application to try to take care of it. So UDP server applications are assigned well-known or registered port numbers. UDP receives a datagram destined for one of those ports. It forwards the application data to the appropriate application based on its port number. The UDP client process dynamically selects a port number from the range of port numbers and uses this as a source port for the conversion or the conversation. The destination port is usually the well-known or registered port number assigned to the server process. And then after a client has selected the source and destination ports, the same pair of ports are used in the header of all the datagrams in the transaction. And you can pause your screen if you want to see this visual here. Okay, so what did we learn in this module? We talked about transport layer. We looked at TCP and UDP protocols. We talked about how TCP establishes a session. UDP does not. UDP and TCP transport layer protocols use port numbers to manage multiple conversations, and each application process running on a server is configured to use a port number. Sequence numbers are assigned in the header of each packet. Flow control helps maintain the reliability of TCP, and the process of destination sending acknowledgments as its process bytes received, and the continual adjustment of the sources send window is known as sliding windows. And to avoid control congestion, TCP employs several handling mechanisms. Okay, I hope this information was helpful for you. Stay safe and be excellent to each other.